Hi, I'm Ben-Yaakov. This presentation is entitled A Modified Magnetic Reluctance Equivalent Circuit and Implication. Now beware, some of the conclusions of this presentation may shatter your intuition because at first look they seem to be counterintuitive. I'd like to thank Evgeny Smidochky for his support in the preparation of this video, and many thanks to Frenetic company for supporting this video and also for their kind offer for a free trial of the power electronics software. Now the details are given in the description section of this video. Now here is a basic transformer, two windings. This is the core, N1 and N2 are the windings, and then we have the input voltage and a load, which is in this case a resistive load. Now this is the reluctance equivalent circuit. I'm not going into it. I'm assuming knowledge of this reluctance. If you are not familiar, I suggest you get the basic information on it. Now what it is that we have here the MMF generated by these dependent voltage sources. This dependent voltage sources is N times I. N is the number of turns of N1, and I is the current or the primary here, the input. And then we have another dependent voltage source, which is N2, I2. Again, it is related to the output in this case, I2, and the number of turns of the output. So these are generating the MMF. So the voltage here is MMF. The MMF is emulated by a voltage and the flux by a current, while the resistor here is actually emulating the reluctance. So we have a flux here, we have the MMF, these are the voltages, and these sources are generating these voltages. And on the interface, the electrical interface, we have again a voltage source, which is a reflection from the flux back to the input. So this is Faraday's law, as a matter of fact, and the phi dt. And the phi, of course, is the derivative of the flux here, and 1 is the number of turns. And the same thing we have at the output. We have a voltage source, which is generated by this the phi dt again, and this time n time. So this is the very basic reluctance equivalent circuit that has been around for many, many years now. Now the basic circuit here sort of looks like a resistive circuit, and this is why this equivalent circuit often is referred to as Ohm's law for magnetics. We have voltages, we have resistors, we have a current. So it seems that Ohm's law is relevant to this circuit. Well, as we'll see, this is just absolutely incorrect, okay? So this is the first thing that we're going to see later on. It is important to realize that at the output section, that is at the output winding and the load, we have here actually a closed feedback loop, because we have here the flux. The flux is affecting this Faraday's law voltage generated, which is causing a voltage here at the output, and then this causes the current to flow due to the resistor, and now this current is coming back here as the voltage of this MMF, and this of course affects the flux. So we have here a closed loop here, closed feedback loop, that first of all is what kind of complicates the analysis, and secondly it might cause some problems in simulation due to the racing here between the signal. So this is one of the problems that one might have with this basic reluctance equivalent circuit. Now, before going into the suggested modification of this circuit, which is the subject matter of this presentation, I'd like to first of all talk about replacement between a voltage source, in this case, and an impedance. If I have a voltage source like I have it here, and there is a current, which is the flux, the current is emulating the flux, then I can replace it by an impedance, and the definition of this impedance will be the voltage across it divided by the flux. Because if we have this impedance here and then you multiply it by the flux, then you'll get a voltage which is the original voltage. Now this is well known in general, and it is used many times actually to emulate a nonlinear resistor. For example, if I have here a resistor, I can replace it by a voltage source defined by R times I. I is the current here. And vice versa, if I have this voltage, I can represent it by this resistor, and this resistor will be V over R. So this is basically what we are doing here, except that this is now an impedance. As we will see, it's not a resistor. So applying this idea, I'm going to replace this dependent voltage source by an impedance. And the question is, what is this impedance? To do this, I am starting with the flux, and then calculating the voltage at the output, the current at the output, and then the voltage that is generated here, this is the MMF source, N times I. Now, assuming that this is a sinusoidal waveform, so we have it like a amplitude of a flux times sine omega c. Now, the derivative of this thing here, this derivative here, is now in the phasor domain, j times omega, the amplitude. And then if I divide it by omega, I see that this impedance is basically an inductor, okay? So what it turns out here, which is kind of an amazing, that you can replace this dependent voltage source that represents the MMF by an inductor. Now, this inductor has a certain value, but it is not linked to the current. So actually, you can sort of erase this thing, and this inductor stands by itself. What it means is that if I have a slab of ferrite, which has a winding on it with a load, this is the secondary side, okay, then the traditional way of representing this will be the reluctance plus this voltage source, the dependent voltage source, which is the MMF, N times I. And now what I'm saying, that you can replace this by an inductor. Now this is in fact a manifestation of Lenz's law. Now Lenz's law tells us that if you have a flux which is generating a current, then the resulting flux from this current will be opposing the original flux. Now this is exactly what this inductor is doing. If you have a flux, you have now an inductor which is kind of blocking this flux, reducing it, you might say. And if the resistance here is very small, then the inductance will be very high, and of course you'll have here a very high impedance that is sort of opposing the flux. So this is just another way to look at the Lenz's law, which is sometimes confusing. But if you look at it this way, that what Lenz's law is saying, that you have here now an impedance which is opposing this flux, well, this makes sense. So now to test this idea, I have here now two circuits. One is the original conventional magnetic reluctance equivalent circuit, and one in which I've replaced this dependent source by the inductor. The value of this inductor, here it is, the N squared times the resistance. Again, I'm putting here this interface here. I can use it to get the current, but actually for the operation of the reluctance equivalent circuit itself, we don't need it because everything is already embedded in this inductor. So this is the basic or conventional equivalent circuit. What we have here is the source. We have here now the dependent voltage source of the EMF. This is the voltage which is reflected to the input. Now ddt is the derivative operator of LT spice. This is an LT spice representation. We have here now this dependent voltage source, which is the MMF N times I is the input current. Now these voltage sources of 0 volts are used for current sensing, you might say, and I'm referring to a current by calling this voltage source. Now these resistors are the reluctances, and then I have here the output side, which again has this voltage source, which is the Faraday's law on this side here, and then I have the load, and this is again the voltage source for the generation of the MMF on the output side, the number of turns times the current of the output. So this is the conventional reluctance equivalent circuit. Now here, everything is the same except for the fact that rather than having this independent voltage source, I have here a passive inductor defined by this value. And now I'm running these together, and here is what I'm getting. Now these are the output currents. What we see here are the output currents here and here, and they are just one on top of the other. They are exactly the same. And then I have here the flux of the two circuits. Again, they are exactly the same. And I have the MMF. This is the MMF at the output side. Here it is. And again, these are exactly the same. So the flux is the same. The MMF is the same. So the two circuits are absolutely identical in performance. Okay, it's not an approximation. It is exactly the same circuit, except that we have now an inductor, a passive inductor, rather than this dependent voltage source for the interface to the output. So what are the implications of this circuit if we now realize that here we have just an inductor? Okay, so we can draw some conclusions here. First of all, the first one is that the flux, it depends only on the input voltage. And this is because we have here an inductor. The inductor is defined by N squared over R. It's independent on the current. So no matter what is the current level, we're going to see the same picture here. Now, the flux here is actually an integral of the voltage here. So therefore, the flux is linked to the voltage only, independent on the current. To show this, I'm running here two cases, one with a load of 10 ohm, the current is 1 amp at the output, and here the load is 10 mega ohm and the current is 1 microhenry. Now obviously the MMF, that is N times I, is much larger here of the 10 ohm because the current is large, and it is much smaller here. But see, what is the flux? The flux is exactly the same. See, the scale here is 330 nanoweber, and this is exactly the scale here. So the flux in these two cases are the same. So the conclusion is clearly that the flux in the core has nothing to do with the current passing through the transformer. Okay? Some may find it, as I've said, counterintuitive, but if you think about it, once you have a voltage imposed on the core, it fixes the flux. Another implication is that the flux is shifted 90 degrees with respect to the MMF. And the reason is that for the flux, we have the derivative involved, which causes a phase shift, while with the current, we don't have a derivative, so there is no phase shift. So if you look now between the MMF and the flux, there is this phase shift, 90 degrees. So calling the reluctance equivalent circuit a magnetic Ohm's law is incorrect, because in Ohm's law, of course, the voltage is the DC. The voltage and the current, there's no phase shift between them, while here you have a phase shift between this voltage source, the MMF, and the current, which is the flux. Now there is another implication here, which is very important, and that is that the MMF are not equal, this and this. This is the voltage here, which is the MMF, is not equal, and they are shifted one with respect to the other. Now, if you look at this circuit, you can come to this conclusion immediately. Because if you have a source here, which is an AC source, we understand this is not DC, okay? And then you have reluctances, which are emulated by resistors, and then you have an inductor here. Obviously, the voltage here is not equal to the voltage here, And not only that, there is a phase shift between the voltage here and the voltage here. Okay? To show that this is the case, I am running again this simulation. And what I did now, I took the difference between the input MMF and the output MMF and look also at the total MMF. This will be the input. And what we see is the following. First of all, there is a difference between the input and the output. Well, there's a small difference as compared to the total MMF, but there is a difference. As I have said, there must be a difference because we have this reluctance, which is sort of attenuating the signal here. And we see here a phase shift between these. If there be no phase shift between the input and output, then obviously this difference would have been in phase here. The fact that it is off means that the output is in some phase shift, in this case 90-degree, related to the input. So what does this mean? Well, you can explain it very easily if you consider the fact that you can represent the physical transformer as an ideal transformer plus a magnetization inductance. So therefore, if you have a current coming in, then part of this current would be circulating here through the magnetization inductance, and then the rest of it will go out through this ideal transformer. So therefore, this current times the number of turns and this current times the number of turns are not equal because of this difference here. Now, for an ideal transformer, this magnetization inductance is very, very large. Now, what does it mean? In the reluctance circuit, it means that the reluctance is approaching zero because a high magnetization inductance means that the permeability, the magnetic permeability, is very high, and it is in the denominator of the reluctance expression. So therefore, the reluctance will be approaching zero, and obviously in this case, the voltage here, the MMF, will be equal to this MMF. There will be no phase shift, but this is for an ideal transformer. In the range transformer, there is a magnetization inductance represented by these reluctances, causing this difference and phase shift. So this effect of the magnetization inductance and the behavior of the physical transformer are really nicely seen when we use this equivalent inductor rather than the dependent voltage source of the MMF. Now, this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest and perhaps it will be useful to you in the future. Thank you very much.